Welcome back. Theorem. If A is non-singular matrix, then A inverse is also non-singular. And the inverse of A inverse is A. This is expected. Proof. Let A be n by n non-singular matrix. What does that mean? A inverse exists and A times A inverse is A inverse times A, its identity. That's the definition of inverse. You multiply to your original matrix, you get identity. But notice A performs the same function for A inverse. That is, A multiplies A inverse to get an identity. That is, the inverse of A inverse is A. The inverse of A inverse is A. So it's a tautology. We are just repeating ourselves. This is how we have proved the theorem. Okay. Now this is an interesting theorem. If A is non-singular, then so is A transpose. The inverse of the transpose is transpose of the inverse. You understand? The inverse of the transpose is transpose of the inverse. Suppose A is an n by n non-singular matrix. Then A inverse exists. And A times A inverse is A inverse times A. That's the identity matrix. Note, the transpose of identity is itself, because transpose is just the symmetric matrix. So you reflect above the diagonal. Well, above the diagonal, when you reflect identity, you get identity back. So take this equation and take transpose of this. Take transpose of this here. Okay. The first line is transpose of this. Second line is transpose of this. Now let's figure out what happens. This guy is transpose. Remember, transpose will change the order. A inverse transpose, A transpose. Well, when you multiply these two, I get identity. In the same way, I transpose this. Transpose changes order. So A comes first, its transpose. A inverse transpose follows. This has to be identity. Why does it have to be identity? Because transpose of identity is identity. Likewise, this identity is nothing but transpose of identity. What does this say? A transpose times this matrix is identity. So this matrix is the inverse of A transpose. So A transpose, the inverse of A transpose is A inverse transpose, which is what we wanted to prove. Okay, it's a very sweet, short theorem. Again, this is an important theorem. You should be able to reproduce, understand this, and reproduce the theorem. Okay. Here is an example. A is 1, 2, 3, 4. We may check that this is the inverse of this. That is, A times A inverse is the identity matrix. By the theorem we just proved, its transpose is also non-singular. And the inverse of the transpose is transpose of the inverse. So, the inverse of transpose of this matrix will be transpose of this matrix. Okay, I hope that's clear. Transpose of this, notice how 1 and 3 halves changed. Linear systems and inverses. Very important short topic. Let A be an n by n non-singular matrix. Then the linear system Ax equals b has a unique solution. How do I solve for x? Multiply by A inverse on the left. X is A inverse of b. In particular, if B is the zero matrix, okay, well, X will be anything times 0 will be 0. That's the only solution possible. Let A be non-singular with inverse A inverse. Ax equals B. We multiply both sides of the equation on the left by A inverse. So Ax equals B, I multiplied here by A inverse and here by A inverse. Notice A inverse times A is identity. Identity times X is A inverse B. But identity times anything is anything. X equals A inverse B. This has proved the first part. You have a solution, X equals A inverse B. Okay. Further, second part, if the B is 0, then A inverse B has to be 0. This is 0, which implies the solution X has to be 0. Okay. An example, solve for X when Ax equals B. You are told A inverse is this, B is this. Ax equals B, how do I solve for X? Multiply on the left by A inverse A cancel, and you have X equals A inverse B. Okay. A inverse A gives you identity. Identity times X is X. So X equals A inverse B. Well, you are given A inverse, you are given B, all you need to do is multiply to get X. 2 times 5 plus 5 times 7. 3 times 5 plus 8 times 7. Alright. Here are homework problems from the textbook for this section. Make sure you go over all these questions before class to ask me questions. Feel free to ask me questions from any page on this particular slide as well in class. See you in class. Until then, bye.